Finally, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. Sorry, I had a lot of technical difficulties this morning, but we are here. So let's make sure I can see the chat and everything. Yeah, I had some activities planned today, but I guess we're just not going to do them because I kind of wasted the time that I was going to do them with. I wanted to put you guys in some breakout rooms, have you struggle against some problems for a while, but we'll definitely do that later. I wanted to try it today. But we will just jump into it. So just so you are aware, the homework, the online homework, you still have some time. So the way things are going, you have some time to get, settled before you have to really be on the grind. Your homework starts in chapter 3. So right now we're in chapter 2. And it's not that I'm going to directly test you on anything we're doing in chapter 2, but it's going to provide you skills that you'll need to calculate and work stuff out in the future, as well as just the act of working out some problems at this level in this chapter. It builds mathematical maturity, it builds problem-solving skills. While you're not going to to address the elephant, well, you're not going to test us on it. Why are we even doing it, right? To address that elephant in the room, it's actually important to build certain problem-solving skills. And for that, oftentimes you need a base of facts and you need a base of rules that govern those facts, and then you need to know how to match and combine these rules. It's a very big thing also when you're doing programming, right? So you're going to come up against things that you've never officially been taught before, and you have to figure out a problem around it, right? And a lot of people think that that's just how you are. You're either someone who can figure out how to do stuff or you're not. But that's not true. Problem solving is a skill that you can build. And so while we're not directly being tested on any of this, I do still think you should take it seriously and just know the rules and how to use them and how to mix and match rules to solve some problem. So last time we spoke about exponentials. We went over the rules. Most of you remembered most of the rules, so that wasn't a big deal. We looked at graphs. We looked at comparing exponentials to polynomials. This is one of the most important things we learned in the last class, that exponentials grow a lot faster than polynomials, even in the short term, though you might not notice. In the long term, the exponential always wins. We also spoke about a real world application, so as to speak, and this is going to be in chapter 3 as well. So I'm going to give you a lot more word problems that have to do with compound interest and simple interest and continuously compounded interest and a lot of other stuff. But just to show you how compound interest leads to an exponential function, which is the reason why we need to understand exponentials, that's important. Now, there are times when actually finding the value of A is not what we care about. So I don't want to know, okay, you invested some money, you're getting this interest rate compounded, and we're doing it for this amount of time. How much money am I going to have at that amount of time? Sometimes that's not the point. Sometimes what we really care about is the time itself. Meaning, if I know ahead of time how much money I want to make and how much money I have now, and what interest rate I can reasonably get on that money, how long will it take for the money I have now to become the money I want, right? So sometimes solving for time is going to be the factor. Now, if you want to solve for the variable in an exponential, this requires you to be able to find the inverse function of an exponential. So it's like if you have, x plus 5 equals 4, what is x? What you have to do is you have to remove the plus 5, so you isolate the x on one side, but what that requires is subtraction. Why subtraction? Because it's the inverse operation of addition, right? So we need to find the inverse operation of exponentiation, and that leads us into our next topic, because sometimes the input is what we want to know as opposed to the output. which leads us over here, which I have some announcements here, but I'll just leave that up. Essentially, that was just me telling you guys that if you haven't heard from, if you emailed me saying that you weren't receiving any email messages from me, then just be cool, assume that I got the email, and on Monday, because I'm getting a new influx of students, I'll just update everyone at the same time. If you didn't email me though, you should. So if you're a new student and you didn't get messages from me through these 4 avenues, you should email me. You guys actually don't really have a problem with this, but I had to elaborate on that with my other classes. But I seem to get pretty good participation in this class, so that's probably not super necessary. So I'll leave that in the notes, but I don't actually think I have to do a lot of that stuff with you guys. Let's get into it. So it turns out the inverse of an exponential is something that we call a logarithm. Okay. Someone give me a chat here. Yeah, sorry, that was a private chat, so I had to take some time to answer that. Okay, so this brings us to logarithms. Now, what is a logarithm? Let's talk about what it is. The logarithm. And I can say the because, as it will turn out, when you try to think of logarithms as functions, they are one-to-one functions. So there's always going to be the answer for some input. You're not going to be in a situation where there are several possible answers. So the logarithm of a number to a given base is the power. So in other words, the logarithm is the exponent, which is that variable that we want to solve for, that the base must be raised to give the number. So that's what it is in words. Let's actually start getting to the math. Let's talk about notation, how you will actually express this. You write log, which is short for logarithm. You write a little number at the bottom. That's going to represent the base of the logarithm. And beside the logarithm, you write the number. And then we say that is equal to the power, right? Or the exponent. Okay. So for example, I can say the logarithm to the base 2 of 8 equals. So whenever I ask, what is the log to the base 2 of 8? The answer is going to be, what is the power I need to raise the base 2 to in order to get 8, right? So the answer would be what?
3.
Yeah, 3. Okay. So log to the base 2 of 8 is 3. Why? Since we need 2 to the 3 to get 8. So you can think of a logarithm as just another way to express an exponential equation. The upshot is, though, it allows us to get the thing here that's in the power down and isolated, right? So it's a different notation that's going to allow us to solve. It's like I gave you the addition sign, and now I'm defining for you what the subtraction sign should look like, right? That's the analogy. Okay, so now that's the logarithm. So let's talk about the laws that govern logarithms. Right, just like how exponents have laws, logarithms have laws. We're not lawless over here. So the first rule or the first law is actually the definition, which is nice, the mathematical definition. So knowing how to maneuver the mathematical definition is the first rule. So this basically says, okay, if I have log to the base a of b equals c, it's the same thing as saying a raised to the c equals b. And that's very important for you to know. That's the definition. That's what's starting this whole thing. Okay. And so now it turns out with that definition, a lot of consequences actually happen. So everything that I'm about to write down, I'm going to give you about 10 rules. They're all based on the fact that that definition is what it is, right? So if I assume that definition is true, that the logarithm actually works this way, there are a bunch of other things that we kind of get as a consequence. For example, if I take the logarithm of something and it's raised to a power, I can actually take that power down and multiply the logarithm, right? Logs turn powers into products. 3. If I have a logarithm and I have a product of things that I'm taking the logarithm of, this can actually split up into the sum of the logarithms. 4, if I have a logarithm and I'm taking the log of a division, that actually translates into a subtraction of logarithms. Okay. Now I want you to appreciate that logarithms are powers, and there is a direct analogy between what I'm writing down here and the laws of exponents that we saw last class. Remember, if you had something to an exponent and you raise it to an exponent, what do? You multiply the exponents, so we can get the exponent n times the original exponent, which was the log. If you multiply two things of the same base, you add the powers. If you divide things of the same base, you subtract the powers. Pretty much we're taking the property that happened in the top right corner and we're making it the main show, right? We want to know what's going on up there down here on Earth. Okay, so the logarithm is actually getting us to do this. And this is actually nice because addition is nicer to do than multiplication. Subtraction is nicer to do than division, right? Multiplying by a number is easier than exponentiating to that number, right? So your logarithm also has the added benefit of making the operations you have to do to get some calculations simpler, which is actually why logarithms were invented. They were invented by this guy called Napier, pretty much for nautical navigation. Back in the day, people used to go out to sea and not return because navigating on the sea is a lot different than navigating on land, and you're covering vast distances, and we just weren't good at navigating those vast distances. So nautical navigation was a real perilous thing until this guy invented logarithms. So now, instead of multiplying distances to figure out how we're going to get somewhere and applying Pythagoras' theorem and all that other stuff, we can actually use addition in place of multiplication. And we can use subtraction in place of division. And we can use multiplication in place of this. And you'll see this in a lot of your science classes, some of your business classes as well. So when you're analyzing stocks and finance things, a lot of times you'll use what's called a log scale. And this is just to kind of tame things down because the data itself is really volatile. So the log kind of cools it down. Instead of things multiplying on top of each other, now they're adding on top of each other. It kind of slows things down so you can see a pattern forming. So it's very important. It's in the background in a lot of things that you're going to do. There's also something called the change of base formula. So this allows us to change the base of a logarithm. Sometimes we're working with a logarithm, but the base that we're working with is inconvenient for whatever reason. So it turns out we have a formula that allows us to change the base. So for, of course, here your A is equal well, A greater than 0, a not equal to 1. You'll see why we can't be equal to 1 pretty soon. So that's the change of base formula. This gets us out of sticky situations like the following. Let's say it was really important for me to figure out what is log to the base 4 of 8. What is that?
2.
Anyone want to chime in?
2.
Like, I see people turning their mics on and then they turn it off. maybe I should have went over this. Oh, are you saying something but I can't hear you? Oh, so is it me again? Yeah, my computer was giving trouble as I was. Did this happen to you guys last time? This happened to one of my classes earlier this week, but I don't remember if it was us. Okay, someone say something again.
You good?
Yeah, I can hear you now. Okay, wow. I was like, man, I was bragging about you guys and you guys went and got all shy on me. No, it was it was me. Sorry. Okay, log to the base 4 of 8, right? So we want to figure out what power do I have to raise 4 to in order to get 8? Okay, so 4 to the 1 gives us 4. 4 to the 2 gives us 16, which is already bigger than 8. So I know the answer is between 1 and 2 somewhere. I don't know exactly where. Is it exactly halfway in between 1 and 2? Or maybe it's like 1 1/4. Maybe it's like 1 and 1.75. Like, how do you know what the answer is? It's just that when I'm thinking of the number 8, base 4 is not really convenient to work with. What would be a more convenient base here, do you think?
2.
Base 2. Why? I know how to express 4 as base 2 pretty easily. I know how to express 8 as base 2 pretty easily. So 2 would be a convenient base. So what I can do is I can actually change this in terms of base 2 by applying the change of base formula. And now what's the answer? What is log to the base 2 of 8?
3.
3. Log to the base 2 of 4?
2.
2. So the answer is 3 over 2. The answer is 1.5. And you can actually check this. Does this work? If I take 8 to the 3 over 2, that's the same as the square root of 8 based on the rules that we learned last class. Cubed, that's 2 cubed. No, sorry. It's 4 to the 3 over 2. If I take 4 to the 3 over 2, that is the same as square root of 4 cubed, which is 2 cubed, which is 8. And so, yeah, if I take 4 raised to the power of 3 over 2, I do get 8. So that actually works out. Okay. Now, the above rules should be memorized. I'd recommend you memorize things. No, that's probably not. I probably don't want to address it that way. I guess I'll do this a little bit later. There are a lot of times where I'll give you guys the formulas to use. You won't have to memorize them. But sometimes I'll ask you to memorize things. And again, it's important. Not everything I ask you to do is going to be obviously important in the moment, but I promise you, I will never ask you to do anything that I don't think is important, where it's like, let me just give them something to do to give them something to do. There's always like a method to the madness. Okay, so the above rules should be memorized, I would say. The following rules will be automatic, but recommended. It is recommended that you memorize them. And conversely, if you practice enough problems, you'll automatically remember these guys anyway, because they'll come up so often. So my calculus class starts out talking about exponentials and logarithms as well, because it's also super important for calculus to understand these concepts. And I kind of tell them, yeah, memorize the first 5 rules and then just do your homework. If you don't automatically memorize these other 5 rules that I'm telling you, you didn't study long enough. You messed up. You have to go back. So here's one of them. Log of 1, right? You should know what that is. Log of 0. Should know what that is. What's log of 1?
0.
0. Why? Because you have to take a raised to the power 0 to get 1, right? So by following the rules, it's kind of, yeah, it's automatic that, yeah, it has to be 0. But it's good to just know that log of 1 is always 0. Log of 0, you should recognize, is undefined. Why? If I give you a positive number like 2, what power do you have to raise 2 to in order to get 0? There is no such power. If I raise it to a positive power, it's still positive. If I raise it to a negative power, I just get 1 over 2 to a positive power, it's still positive. If I raise it to 0, it becomes 1. So I'll always be positive no matter what. If I have a positive base, I cannot change the sign or make it 0 with a power, right? So getting to 0 is, it can't be done. In fact, log to the base a of x is undefined, also if x is negative, for the same reason. Given a positive number, there is no power I can raise it to get 0 or something negative. And we're always assuming our base is positive. So that's that. Here's one log to the base a. And this one is pretty also straightforward if you think about it. What power do I have to raise a to in order to get a to the x? Well, x, right? X is the power, right? And this one is not as straightforward, but it's cool to know. You can prove it, but it's not going to be obvious just by looking at it. If I take a base a and I put a logarithm in the power, and the logarithm has the same base as the big base down at the bottom, then they kind of cancel each other, right? This is the part that's important for solving equations, right? So when I mentioned that goal of being able to solve for the time in the compound interest formula, these are the properties that make that possible, right? So essentially, if I wanted to get to the x up here, I know that if I wanted to get to the x up here and I'm given an exponential, I can hit it with a logarithm to get that x. Right, so this is the thing that tells you, oh, I can use logs to cancel exponentials and I can use exponentials to cancel logs. So this is what shows them important for solving equations. These show log to the base a of x and a to the x are inverse functions. So essentially, I just want you to be aware that, okay, if I have an exponential and I want to solve for the power, I should use a logarithm. If I have a logarithm and I want to solve for what's inside the logarithm, I should use an exponential, right? Just like how you know, if I'm solving an equation, there's plus something on this side, I need to use subtraction. If there's minus something on this side, I need to use addition, right? You just know what to do in order to get out of a certain sticky situation. Now, the 10th thing I want you to know, it's more of a notation thing. But it's also important to know if I write log to the base e, this is called ln. If I have just log, this really means base 10, but I didn't write it. Now, this kind of varies based on your discipline. For a computer scientist, if they just write log and they don't write the base, they really mean base 2 because of binary, right? Engineers and almost everybody else use base 10 because they, 10 fingers, everyone wants to make math as easy as possible to count with their hands. Mathematicians, though, use something that's called base E. Now, E, I don't remember if I told you guys about this. I definitely told my calculus class about E. E is a constant. Very important. E is roughly 2.71828. It's a non-repeating decimal, meaning it is an irrational number. You cannot express it as a fraction. And it was discovered by, did he discover it? I know he was the first person to calculate it to very high precision. I don't remember if anyone before him, let's just say it's named for, that's definitely true. Named for the Swiss mathematician, many people's favorite mathematician, Euler. You'll hear a lot of your science friends call this Euler, especially your biology friends. That's not how it's pronounced. He's Swiss, but he is an amazing mathematician, one of the most prolific mathematicians that we know. A lot of the math that we know today was due to this guy. So how did it come about? So Euler studied this situation. You invest $1 into an account, compounded continuously. And like I said, in chapter 3, we'll talk more about this. So if you don't get what I mean by compounded continuously right now, it's okay. Basically, that means that we're paying you interest an infinite amount of times per year, right? So it's not like we wait till the end of the year to give you your interest and add that to your account. We're the whole time you're holding the money, we're constantly paying interest on that money, right? So it's like, you're like, wow, this is going to grow fast. It's compound interest. It's going to be exponential. It's going to, oh, man, I'm going to have like infinity dollars. Okay, which eventually you would if the world lasted. But anyway, compounding continuously at, and we really crank up the interest rate also 100% interest. Right. Now your credit card will hit you with somewhere between 18 and 22%, which is enough to put a lot of people into debt and ruin their lives. But let's say we're paying you 100% interest continually, every second of the day, every half second of the day, every quarter second of the day, every millionth of a second of the day. I'm going to look at how much money you currently have and put interest on top of it, right? Now, the question was, how much money would you have at the end of a year? Well, a lot of people who realize what an exponential function would be is like, dude, I'd have infinity. Turns out the answer is no. Turns out the answer is you'd have $E at the end of the year. So you'd have roughly $2.72 under these conditions, right? And that was what Euler figured out. And he figured it out to many, many decimal places. And it turns out E is a very important number, kind of like pi. You know how pi is everywhere and everyone geeks out about pi? You have an equally passionate group geeking out about E. I don't know, they're not wrong. They're probably more right than the pi people, to be honest, if we're comparing you know, the fanboys. The E people probably has a lot of things. Also, a lot of things going for them. Also, many believe y equals e to the x. This is called the natural exponential, because it's very natural to use it in mathematical context. It's called a natural exponential, is the most important function in mathematics. For sure, it's the most important function in calculus. There are a lot of people who would say push it beyond that. So it's a very important number, and it leads to a very important function. All the things we know about calculus, we would not know without this function. A lot of the rules of calculus and how things grow and how we measure change is based on the behavior of this function. The math we know, we'd either not know it, or it would be considerably more complicated if we didn't know about this function. So it's very important. And Euler came up with that number, e. Okay, and so when I mention here log to the base e, I'm talking about log to this number, right? So it's a constant like pi, yeah. So even though it looks like I'm writing a letter, it's really representing a number. When I write pi, everyone knows, oh, it's 3.14159, right? E, when I write that down, I also mean a number. And you'll see this again in chapter 3. Graphs. Laws 8 and 9 show us that logs and exponentials are inverses of each other. So we know how to sketch the graph for free. So we know that inverse functions have this property when if you take the graph of a function and you put the line y equals x and you mirror reflect that function over that line, you get the picture of its inverse if the inverse exists. So because we know how to graph an exponential function, we automatically know how to graph a logarithm function, right? So because last time we saw that we know that an exponential function y equals a to the x looks like that, I know that if I were to draw the line y equals x and just reflect that, that gives me the line of the logarithm function. So this would be y equals log to the base a of x. Okay, and this one passes through 1 because that one passes through 1. So you get the exact mirror image over the line y equals x. So this leads to, again, assuming a is greater than 1, y equals log to the base a of x. That graph looks like this. Let's just draw some transformations. That looks like that. Right, remember what's inside a log cannot be negative. So if I have a negative x inside the log, then the x's themselves have to become negative in order to make it positive. So we get the graph on the left side. Y equals minus log to the base a of x. Of course, this means it flips upside down. And y equals minus log minus x. Okay, so those are all the log graphs. You guys a few seconds to copy that. I guess take a picture or whatever. So another important, well, I mentioned this important fact later, but I'm going to be generalizing on that fact. So earlier. So last class I mentioned that exponentials grow a lot faster than polynomials, like way faster than people think. You just have to wait a while for you to see it sometimes. The same, we can actually put the logarithms on a hierarchy as well. Let's put them on the same chart. Important fact. Log to the base a is much smaller than x to the a is much smaller than a to the x as x goes to infinity. So the same kind of relationship that an exponential had with a polynomial, where it's like way out in infinity, the polynomial might as well not even try because the exponential is way high and the polynomial is effectively zero. That relationship is held between polynomials and logarithms. So if you're having a polynomial competing with a logarithm, the polynomial is going to be like way up here. The logarithm might as well not even try. But then the exponential is way on top of both of them, right? So it's like this Russian dolls of really, functions getting more and more crazy, right? So logs grow slower, which is why people use log graphs. When you're charting stocks, you look at log returns, because when the stock is going crazy, the log brings it down. So you can see what's really going on here. And you can actually measure things easier that way. So logs will grow slower. They're more manageable. We can measure them with less computational input. And so that's very important. And what I wanted to do today, a part of the activity I wanted for you guys was I wanted you guys to work on some problems together. But since we had technical difficulties, I guess that's not going to happen. And like I said, I'm not really going to directly test you on a lot of things like this. I mean, the thing that you would have to know for the future, like the closest things that would be like relevant to what we'll be doing are like these two simple equations here. But I really think training your problem solving muscles is very important, especially for figuring out things that I'm going to have you guys figure out in the future. So while I'm probably never going to directly ask you to just calculate some random equation with logs and exponentials, knowing how they behave is going to be very important, so that when you do have to do it, it's just so easy for you to do it. You can do it with your eyes closed, right? So the kind of exponential and logarithm calculations you'll have to do for a compound interest problem, for example, is not going to be as complicated as these problems here. But if you can handle these problems, then you can definitely handle those problems. And they'll be a lot easier by comparison. So instead of rushing through these, I think I'll leave these up. I'll have you guys try them. We'll go over them quickly on next time we meet Tuesday, I want to say. So we'll go over them quickly on Tuesday, but I'll ask you guys to try these. And yeah, I'll leave them over here. So I'll print them in the notes. What I would do just to wrap up is, since we didn't get to do our class activity now, maybe what I'll do for the next 2 or so minutes is to actually put you guys in breakout rooms anyway. Are you guys all in the same cohort or? No, okay. So what I would do is I'm gonna just randomly split you guys into breakout rooms anyway. And what I would recommend you do is just like get each other's contact information, or maybe switch, exchange phone numbers and get into a WhatsApp group, just to get like a preliminary study group growing, and you guys can help each other out on these problems for next week, and then we'll wrap up. So I will do that. I'll give you guys like 2 minutes to just get a little group going that you can kind of chat about these problems with. And how many people do I have? Okay, so I am going to do it now, okay? So I'm splitting things up, so there are going to be 3 to 4 of you in the room. I would recommend that you get each other's contact information and work on these problems together, and we'll go over them next week. I'll pull you guys back after 2 minutes, and then I'll let you guys go. So now you should see like an invitation pop up on your screen to join the room, and just head on into that room. And I'll see you guys soon. Okay. Let me stop recording at this point, and I will see you guys soon. Okay, it seems is everyone back? Everyone will be back in like 20 seconds. Me? Oh, someone asked me to scroll down. Maybe that's better.
Will you post something on Blackboard about these problems?
I'll post it in the notes for the class that's posted with the video.
Okay.
So remember, I post a PDF of the notes on the video. So if you don't get all these down right now, it's actually fine. It's more important that you got the contact information for everybody. But it seems like everyone is back. So yeah, I brought y'all back to basically say goodbye. I didn't just want to kick you guys out. Have a good day. Sorry for the technical difficulties earlier. And I will see you guys in the next one. Ciao.